Assalamu alaikum. Can anyone explain to me in very simple words what is the uncertainty principle? All right, ideas. Anyone from there? पीछे से कूदा आप बताओ जी. Right. So whenever the particle's momentum is known, its location is unknown, and when its location is known, its momentum is unknown. It's not unknown, there is a spread in the values. That is, there is some uncertainty or ambiguity in what precisely what the momentum of the particle should be if its location is well known. But remember, when we say the word particle, whenever we mention the word particle, I did not intend to talk about this today, but I cannot resist talking about it. Whenever we use the word particle, we face this problem of the limitations of language. A particle is a word, or corpuscle is a word which exists in our language, in the English language, without the concept of quantum mechanics. We need not be physicists or practitioners of quantum mechanics to know what a particle means. So this word particle shapes our notions of what an electron is, what a photon is, what a neutron is, what a proton is, and what other quantum objects are. But we should not be restrained by this terminology. This terminology is at times misleading. जब हम पार्टिकल का लफ्ज़ इस्तेमाल करते हैं तो हमारे जहन में एक spherical object की इलामत आती है कि it's something which has a spatial extents, it is something that spreads over space, but it is finite, something that can be drawn. If we ask someone to draw a particle, it looks like a sphere. But when we talk about matter waves, we thought that the matter wave is a pulse or a wave packet, and when the wave packet is moving, the particle is moving with it, and that is where the word pilot waves come from. So if we have a wave function, or if we have a pulse which is given by fx, and fx minus vgt is how this pulse will move in space with the particle. You see, x is the position, and if we also talk about the time variation of this matter wave, we have to put in a vgt as well, where vg is the group velocity. So this is the mathematical form of the matter wave associated with the particle, and when the particle moves forward or backwards, the particle comes here, the matter wave associated with the particle also moves with it. So that is why we call these waves pilot waves. But this is also a limitation of our understanding. We should not look at these pictures too literally. That is, there's a particle going and there's a wave moving with it, and the particle is riding on top of the wave. So these are just conceptual tools to understand what is happening, but these pictures do not have an objective existence in the real world. What quantum mechanics is all about is that it is a field that fills space. All matter is a field that fills up space. So this is a very profound statement. The most accurate theory that mankind has ever come up with is called relativistic quantum mechanics or quantum field theory. And what we are studying in this course is the non-relativistic limit of this field theory. And according to this theory, if you have a single electron, for example, an electron that is passing through a double slit interference experiment, that is, you have a slit S1 and two slits S2 and S3 that are carved inside a barrier, and then you have a screen here. So this is the diagram that we've seen so many times, and then you have a filament that is ejecting electrons. These electrons move through slit S1, they move through S2 and S3, and they form an interference pattern on the screen. So this is the experiment that we looked at in the first lecture. But then these electrons, first we talked about the electrons as being particles. पहले हमने ये देखा कि the electrons are particles. So a particle moves in time, it passes through this slit, it passes through slit S2 or S3 and then falls on the screen. But that should not give an interference pattern. Then we said, no, the electron is not a particle. The electron is behaving like a wave. So what we thought was that there is a matter wave associated with the particle, and as the particle is moving forward, we can forget about the particle and think about the matter wave only. So the matter wave is passing through the slit S1, and then it splits up into two parts. It passes through slit S2 and S3 at the same time, and then it forms an interference pattern. But the problem with this picture is that the interference pattern disappears if we would like to tell which slit the particle is passing through. That is, we make an observation on the location, the precision of the momentum disappears and the interference fringes disappear. So the most exact or the most faithful description for this experiment is that when a single electron is passing through the system, you cannot tell where the electron is inside this system. You cannot tell where the electron is. At any instant. Because the electron is not really a particle. What you can say is that the electron is a field. It doesn't matter what kind of field it is, but it's a field. Suppose you have an electric charge, you place an electric charge inside the room, its electric field appears. So you have a charge, a positive charge. Suppose you have an atom, you knock off an electron, it becomes a positively charged ion, and instantly, within no time, within zero time, an electric field appears. And the electric field extends in space. And the constant electric field lines, they are given by circles. So the electric field is constant along on these points. It's constant in magnitude because these are isopotential lines. So the electric field is immediately established because of this particle. Now there's a particle and there's a field that is filling up space. Now you can talk about the particle or you can talk about the field. It's one of the same thing. And the field extends throughout space. And you cannot tell when the field, you cannot say that the field is traveling in space. The field is always there. So the particle is a local concept. The particle is a local concept. That is, the particle must exist somewhere and it must exist at some point in time. So the particle is a local concept, but the field is a non-local concept. The field is a non-local concept. That is, the field fills up the entire space. And this is a correct picture of how the particle is behaving. And this describes what happens in reality. Similarly, when an electron is passing through this double slit, do not think of the electron as a particle, or the electron has a matter wave that is moving, riding with the particle, or the particle is jockeying the matter wave. It's not like that. When an electron is passing through this slit, even if it's a single electron, then there is a field in this region. There is a field associated with that with the particle, and that field is generally denoted as psi. Psi. This is how you denote this field. This field is a function of position and it's a function of time. And this field exists everywhere in this apparatus. This field exists everywhere in this apparatus. And it's not that the particle is moving through the apparatus and some kind of wave is traveling with the particle, or the particle is moving and you can have a microscope and look at the electron at different points in time. In order to observe interference fringes, you have to assume that there is a field inside this apparatus. And if this apparatus is inside a black box, and it is impervious to observers, that is, observers cannot look into the black box, and the electron cannot come out. There's no messenger coming out of the black box, and there's no messenger going into the black box and seeing what's going on. Then this field will exist at all times. However, when you place a detector here, you are disturbing the system. The system doesn't want to wake up. You give it a wake-up call. You're disturbing the system and you're observing the system. Now you are intruding the system. आप दखल अंदाजी कर रहे हैं नेचर में. तो जब आप दखल अंदाजी करेंगे नेचर में, this field will collapse. The field will collapse. And when the field collapses, all of the energy that is carried inside the field, it collects, it bunches up and appears on the detector. It's a very strange concept. देखो, जब ये interference experiment को हम study कर रहे हैं, we are assuming, we say that there is a field inside the apparatus. It's really a quantum field, and that is what you study in quantum field theory. So there's a field inside the system that is denoted by psi. It's a function of position and time, and that field exists throughout this region. It exists everywhere. Even though the electron, when you think of the electron as a particle, it is moving through the apparatus. If the electron were a particle, at time t1 it would be here, at time t2 it would be here, at time t3 it would be here, at time t4 it would be here, because the particle has a velocity and it's moving in space. But this is an inaccurate picture as far as quantum mechanics is concerned. The most accurate picture is that in the quantum world, every particle, so-called particle, has a field associated with it, which extends throughout space. And it is a non-local field. It extends throughout space, denoted by psi. And the very act of making an observation collapses this field. That is, all the energy that is inside the field bunches up into a discrete unit or a discrete packet and impinges on the detector and transfers all its energy to the detector, and the detector clicks. It gives a sound or it gives an electrical signal. And that is what we mean by a particle. Because when we are making an observation, there are many questions, I'll answer them. I'll give time, please. When you're making an observation, what is happening is that the field is collapsing. All the energy is bunched up and is imparted to a detector, which could be the human eye as well. And it is this concept of bunching of all the field's energy into a packet that we give the name particle. This bunching is called a particle. Because particle, we are at the liberty to choose our words. We are human beings. And languages are shaped over thousands of years. We are at the liberty, we are in the driving seat as far as language is concerned. So we give this act of bunching up of all the energy of the field into a unit, into a discrete unit, and it's collapse onto a detector. We call it a particle. So this collapse tempts us to use the word particle. So this is one conceptual difficulty that students always face, physicists also face, and teachers also face this conceptual difficulty because it's a difficult concept. It's a difficult concept to grasp because we are human beings and these concepts are counterintuitive. They do not match our experiences and our notions of language. So quantum mechanics is really non-local. There's a field associated with the particle. That field is called psi. And in the remainder of this course, we will see how this psi changes with time and position. That's the Schrödinger equation. That's the non-relativistic version of quantum theory. And the act of observing collapses the energy into the notion of a particle. And that is what we observe. So this field exists throughout space. It's totally non-local. But when we place a detector here, this is in the region of a bright fringe, all the energy is deposited onto this detector whenever this detector clicks. And the other strange thing is that if you have one electron passing through the system, followed by another electron, followed by a third electron, now all of these electrons are identical. They are like twins. Two electrons are like twins. You cannot tell the difference between two electrons. They are fundamental particles. The first electron has to be identical to the 100th electron, to the 50th electron. All electrons are identical, right? But then the electrons are not behaving identically. You place a detector here and you place a detector here. Sometimes this detector clicks and sometimes this detector clicks. Now if all the electrons are identical, why don't they show identical behavior? Why don't they always fall onto the same detector? And that is the very inherent randomness that lies in quantum mechanics. And where does that randomness come from? That randomness comes from the fact that you have a field and you're collapsing all the energy into packets, and there's a probability that a packet will be deposited here or a packet will be deposited here. So this is inherently random. There's nothing, you cannot blame the experimenter that he is using a sloppy detector here, or the detector has noise, or there's some error in the detector, or he's making a faulty observation. Even if these are perfect detectors, the electrons will not behave identically because the process itself is naturally random. It's uncertain, and that uncertainty is captured by the uncertainty principle. Now there's a horde of questions, so I will give 3 or 4 minutes to answering questions. पहले यहाँ किसी ने सवाल पूछा था, आप बताएं.
So when we are saying that the electron is a field, how can we shoot a single electron inside the system? And the second question, that if it is, you're saying that inside the system it is a field, but we have no way of checking whether it's a field or not. Once we check it, then the field will collapse. And how are we so sure that it really is a field inside the system?
So the student has asked a very interesting question that borders on physics and philosophy. The question is, how are we sure that there is a field inside the system when we can't measure it? Because when we make a measurement, the field collapses. All right. Now this is a field. When we are making a measurement, we are collapsing this field. That is, all the field collects its energy into a packet and deposits itself on the detector. Now how do we know that such a field exists? We know it because we can perform a large number of experiments that can test that this field really exists. First, when we talk about fields, then there's an interference pattern that is detected, which means that the field has a definite form. The field has a structure to it. And what is the structure? The structure is that this field is a combination of two kinds of fields. Psi 1 and psi 2. And there is a phase associated with each field. And when you are making a measurement, you are collapsing this field. And the collapse is represented by psi complex conjugate multiplied with psi itself. Now this gives you a pattern, and that pattern is proportional to cosine square theta 1 minus theta 2, which is simply this interference fringe. Therefore, by looking at the interference fringes, you can tell that a field exists of this form. So I wanted to answer this question in later sessions, but since you have caught me on the ground, this is the kind of reasoning that is used to tell that a field really exists. Even though the field cannot be seen directly, but when you are making a measurement, you are measuring a quantity that is called the modulus squared of the field. So this is the point of collapse, but I will look at this in more detail in later classes. More questions? Ji. देखिए एक चार्ज पार्टिकल है, ठीक है, इन स्पेस. अब उसकी इलेक्ट्रिक फील्ड एग्जिस्ट थ्रू आउट द यूनिवर्स. So the particle is confined to a particular position in space, but the electric field is global. It exists everywhere. That is what I wanted to say. Any more questions? Ji.
So is the concept of the field only associated with a free electron, or an atom consisting many electrons can also comply to this field?
Every particle has a field associated with it.
So then why does at a macro level it appear just as an object? Why is it just not field, atoms are not field? How do interactions between electrons and atoms take place as a concept, as a object concept, on an objectual conceptual basis?
Okay, the question is, why don't big objects act like small particles possessing these quantum properties? Most of you should be able to guess an answer to this. Why isn't the quantum behavior so apparent with macroscopic objects?
Because they cannot attain the speed of light. That's one of the reasons.
No.
Particles apply classical mechanics.
Why is that?
Because attaining the speed of light is sort of becomes difficult for them because the mass inertia is much more.
Or in other words, you can talk about lambda equals h over p. The value of h is so small. The smallness of h prevents quantum behavior to be apparent in the macroscopic or classical world. Massive objects, bigger objects with a larger momentum have a much smaller wavelength, and it is difficult to diffract these objects. So when you have a very small wavelength which is smaller than all the observational, for example, if the wavelength is of the order of 10 raised to minus 30 meters, you cannot perform any experiment that we know of today that can detect such a small wavelength. Therefore, the quantum behavior does exist. It becomes imperceptible because of the smallness of h.
So that I understand, but if at a grassroots level it's a field and not an object, then how come at the macro level it converts into an object? That is my question. If you're saying it's a field independently, it's such a small object at a small level, it's a field, not an object, then how come when a collection of stuff increases its mass, it becomes an object and not a field?
Well,
a field, how does it convert into an object? That's my question.
Well, a massive object will also have a field associated with it. But if you look here, the field has a dependence on r and a dependence of time. Smaller objects will have fields that are spread out in space. Bigger objects will have a field that are confined in space. So they will have fields, but in order to observe the field behavior of such massive objects, you will have to go to that small microscopic level to observe the field. So they do have fields, but they are imperceptibly small.
So why does it collapse?
Now the question is, why does the field collapse? You see, quantum mechanics really borders on philosophy at one level. Why does the wave function or why does the field collapse? We have no answer to this. Neither do we have a mathematical proof that the field collapses. This is a so-called postulate that the field collapses. In fact, there are two theories about observing quantum systems. The first theory, which I've hinted at today, is the collapse theory. It's also called the sudden death theory. It's also called the Copenhagen interpretation. In the Copenhagen interpretation, you have a wave function or a field psi and when you make a measurement, this field collapses into a so-called particle, and that is what you observe. That is, you observe a discrete packet of energy. Observation is just measuring energy, remember that. You're transferring energy to a detecting device. For example, if you're measuring current, you're transferring energy to a galvanometer or an ammeter. You're measuring voltage, you're transferring energy to a voltmeter. That's how a measurement device works. So all the field is bunched up into a packet, a so-called particle, and is deposited onto the detector. The wave function collapses. After the detection has been made, there is no field. The field vanishes because all of it has gone into the detection process, and this measurement collapses. Psi. The other interpretation is called the many worlds interpretation. In the many worlds interpretation, what is happening is that if an observer is making a measurement, the field collapses. Let's move back to this experiment. There are two observers. One is observer number 1 who's sitting here. The other is observer number 2 who is sitting here. When the field collapses, either this detector clicks or this detector. And it's a random event, whether this detector clicks or whether this detector clicks. Now, in one experiment, this detector clicks. The field has collapsed its energy and interacted with an atom on the detector at this location. In another experiment, this detector clicks. So the field has collapsed its energy and interacted with the detector in this location. So this is the first interpretation, the Copenhagen interpretation or the collapse interpretation. The second interpretation is that if this detector clicks, then at the same time another world is created in which an observer is observing this detector to click. So this is called the many worlds interpretation, and of course you'll laugh on this and you'll scoff on this, but there are physicists who seriously think on these lines. And this is called the many worlds interpretation. That is, two worlds at the instance of measurement. Two worlds are created. You live in a world you live in a world in which this detector clicks, and there is some alter ego, someone else living in another world who's detecting this detector to click. So this is called the many worlds interpretation. So the universe is created, a new universe is created every time you're making a measurement. और इसकी philosophical theories बहुत सी हैं जो इस तरह quantum mechanics से पहले इस तरह की आइडियाज प्रेजेंट करती थी. उस थ्योरी को कहते हैं ओकेजनलिज्म. हाँ जी. So the question the student has very rightly asked is, if the electron has kinetic energy, what does it mean for the field? Well, we are going to study an equation that answers this question, and that equation is called the Schrödinger equation. So you'll have to bear for me for a couple of lectures to explain this.
I have a question. The theory that we have just studied about the collapse theory, we believe that it is the absorption of energy on the detector that causes the disappearance of the field. If we assume that we have an ideal detector that does not have any kind of absorption of energy, would we be able to observe quantum effects practically?
You see, the student has asked another very beautiful question. I'm really amazed by the kind of questions you're asking. First of all, he said, if we can build a detector that does not absorb energy, can we look at quantum effects? The first part to this question is, yes, we can make detectors that absorb little energy and disturb the system to a smaller degree. These are called weak quantum measurements, and they routinely take place. But if you have a single electron or a single particle and you're doing experiments with a single particle, this weak measurement will not work. You'll have to do a strong measurement because the electron cannot be split up. If you have a large number of electrons and an ensemble of electrons, these weak measurements do work and they do not disturb the system. That is what happens in certain forms of spectroscopy. The second point is that the collapse of the wave function does not immediately tell you that we cannot observe quantum effects. We can observe quantum effects. This interference fringe is a quantum effect. You will agree with me that this interference fringe cannot be explained classically. This is a quantum effect. Even though you are depositing the energy on detectors and you are collapsing the wave function, still you are seeing an effect that cannot be explained classically. So having a projective measurement or a strong measurement that collapses all the energy on a detector does not say that you cannot observe quantum effects. Quantum effects are routinely observed. In fact, in lab 3, students perform an experiment with superconductors that looks at quantum effects at the macroscopic scale. So quantum effects are observable. ऐसी बात नहीं है.
What I said is that if I have an ideal detector at D1 and an ideal detector at D2, would I observe electron as waves or a particle at one of the detectors?
When you are depositing energy, the electron comes as a bunch of energy. It comes as a bunch. It comes as a parcel of energy, and all of the energy is concentrated into this deposition. So that is what we mean when we say a particle. So it's detecting the electron as a so-called particle. चलिए अब हम थोड़ा सा आगे चलें, फिर हम आपकी क्वेश्चंस का बाद में जवाब दे देंगे, लेकिन आप बार बार हाथ खड़ा कर रहे थे, आप पूछ लें. Yes, so people have all kinds of corollaries with this. So they say that the new world that is created is a parallel universe, and you can tunnel into the parallel universe.
And also the first concept in collapse theory of Copenhagen interpretation have something to do with Schrödinger's cat experiment.
Yes, it's the same thing as the Schrödinger's cat experiment.
So can we say that the addition of energy creates mass?
The addition of
Energies create mass. Because what is confusing is the fact that a single electron is a field. So what I believe that if many fields join together they create mass, and that is why at macroscopic level we have objects.
yes, so when we talk about the deposition of the energy, the electron is now disappearing. Its mass has to go somewhere. That mass has converted to energy and is now converted into the electrical signal from the detector. That's what is happening. So here you have the quantum world. Here you have the quantum world, the detection process or the collapse, you enter the classical world. And we are classical beings. In order to look at experimental observations, we have to live in the classical world and observe the quantum effects. So that's why quantum mechanics is so strange. But let me come back to the intended topic of today's lecture, which was applications of the uncertainty principle. And I'll talk about 2 or 3 applications, very interesting applications. The first question I would like to ask you, why can't we squish or squeeze atoms? We know that most of the atom is empty. We already know that the nuclear size is much smaller than the overall size of the atom, as Rutherford told us. Then why can't we compress the atom so that it assumes a very large density? या हम ज़मीन पर चलते हैं. What prevents us from compressing the earth? ये ज़मीन हमारे पाँव तले धंस क्यों नहीं जाती? क्या वजह है? या एक और सवाल आपसे पूछता हूं. We have a nucleus inside the atom and the nucleus is positively charged. Plus Ze is the charge on a nucleus. Now there's an electron, a lone electron, which has a certain energy. Now the energy of the electron is minus 1 over 4 pi. The potential energy of the electron is minus 1 over 4 pi epsilon naught Ze squared over r. Now the energy can be lowered by decreasing r. The potential energy can be lowered by decreasing r. So the potential energy is 0 at the center of the nucleus. Why doesn't the electron come into the nucleus and fall into the nucleus? Bohr postulated that there are certain orbits in which the electron can move, but we do not have a physical motivation for this fact. Why doesn't the energy lower itself? Why doesn't the electron fall into the nucleus and the atom is squeezed as a whole? So what we expect classically is that if this is R and this is the energy, what we expect is that if R decreases and you have a classical particle, the energy decreases according to this expression. So it is preferable for the electron to be close to the nucleus. But what is preventing the electron from falling into the nucleus? It is in fact the uncertainty principle that is preventing the electron from falling into the nucleus. It is the uncertainty principle that is preventing us from squishing atoms or from compressing atoms. And in fact this explains why neutron stars are formed. This explains why proton stars are formed. This phenomenon explains how white dwarfs, which are big stars, are formed. So the external pressure the external pressure on the electron that is preventing the electron from falling into the nucleus is in fact of quantum origin. It cannot be explained classically, because for a classical particle you would expect a very small energy if R goes to 0. That is, you expect the electron to fall directly into the nucleus. But how do we use the uncertainty principle to show that this is not the case? Well, it's simple, just a long string of calculations. Suppose we have an electron. The energy of the electron is given by half mv squared minus, let's suppose this is a hydrogen atom, half mv squared minus 1 over 4 pi epsilon naught E squared over R. Now the electron has a momentum. Suppose the momentum is P and the electron is at a distance R from the nucleus. Now we have the uncertainty relationship, which tells us that the uncertainty in the momentum times the uncertainty in the position R is greater than h bar over 2. So let's suppose that this is of the order of h bar. Is greater than h bar over 2, it's of the order of h bar. ठीक है? अब इस एनर्जी को मैं p स्क्वायर ओवर 2mv लिख सकता हूं, काइनेटिक एनर्जी को. Now suppose the uncertainty in the momentum is of the order of the momentum itself. कि जो मोमेंटम है इलेक्ट्रॉन का, अनसर्टेनिटी भी मोमेंटम जितनी है, यानी डेल्टा P over P is about 100%, which means delta P is of the same order as the momentum of the electron. देखो हम यहाँ पे estimate कर रहे हैं सिर्फ. We are working with estimates. We assume that the uncertainty in the momentum is of the same order as the momentum itself. So the uncertainty in the radius is of the same order as the radius itself. So using these estimates, we can write PR is of the order of h bar, or P is of the order of h bar over R. So we can insert this value of P, which comes from the uncertainty relationship, into the energy, and we get h bar squared over 2m r squared minus 1 over 4 pi epsilon naught E squared over R. So this is the energy of the electron. Now what I would like to do is I would like to see if this energy has a minimum. In this classical case, the energy does not have a minimum. You decrease R, the energy keeps on decreasing. The energy keeps on decreasing. This is what you would expect if uncertainty principle was not at work. But if uncertainty principle is true, we would expect this energy to have a minimum. And that minimum will exist when partial E over partial R is 0. So you find the minimum for the energy Oh, sorry. I'm sorry. ठीक है? ठीक है? अब डेरिवेटिव आप चेक कर लें ठीक किया मैंने कि नहीं. So there is a value of the radius for which the energy is minimized. And if the radius, if r is smaller than the radius, r min, then the value of the energy goes up. And you can prove by taking the second derivative that this is indeed a minimum, not a maximum. And if you notice from our discussion of the Bohr's model, this expression is luckily exactly equal to the Bohr's radius. Luckily. This is just by fortuition. I mean, this is just out of luck, sheer luck, that we get an expression equal to A naught, and that is because we've used an approximation. PR is of the order of H bar. We could have used H bar over 2 as well. In that case, this will be not be equal to A naught, but it's of the same order of magnitude, because we are making order of magnitude calculations here. So at this particular radius, which is close to the Bohr's radius, is the energy minimized, which means that on this curve, for a quantum particle that is obeying the uncertainty relationship, as radius decreases, the energy goes down, but at a certain value of radius, which is r min, which is of the order of the Bohr's radius, the energy takes a nosedive in the upward direction and the energy goes up. So corresponding to this radius, which is of the order of the Bohr's magnitude, there is a minimum energy of the electron, and that minimum energy of the electron is simply minus 13.6 electron volts. That is why Bohr's calculations start making sense. The smallest radius at which the electron can exist is the Bohr's radius. If you try to bring the electron any closer to the nucleus than the Bohr's radius, its energy goes up. The uncertainty in the momentum goes up according to the relationship that we've written. If you decrease r below a certain value, the momentum goes up. And when the momentum goes up, the electron cannot be confined to the small radii that we expect the electron to be. That is, we cannot bring an electron into the nucleus. An electron cannot exist inside the nucleus or very close to the nucleus, because if we try to restrict the position of the electron close to the nucleus, that is, we want to bring it closer, the energy goes up, the uncertainty in the momentum goes up, so the momentum has to go up and it will fly away from the nucleus. So an electron cannot exist inside the nucleus or very close to the nucleus. That's why in beta decay, when certain elements decay and they emit electrons, The electrons are not coming from inside the nucleus. The electrons are coming from a neutron that has decayed, forming a proton, an electron, and an antineutrino. So the electron that is coming in the beta rays is from the disintegration of a nucleus, but the origin of that electron is not from the nucleus. So that is why another important point, when we have particles, when we talk about electrons, they cannot exist close to the nucleus, but there are particles inside the nucleus. There are particles inside the nucleus. There are neutrons and protons inside the nucleus. And there are particles that hold these particles together called gluons. Now when we talk about particles inside the nucleus, the energies associated with these particles is very high. Because now these particles are confined to a smaller region in space, the nucleus. Therefore, the uncertainty in momentum must be very high. And if the uncertainty in momentum is high, the momentum should be high. The momentum should be high implies that the energies should be high. So when we talk about nuclear particles inside the nucleus, they generally have very large energies and large momenta. But what holds them together are other strong nuclear forces. So uncertainty principle is at work here. That is, the electron cannot exist inside the nucleus, and the electron cannot be brought into the nucleus, the atom cannot be squished together. And there is an external pressure. देखो gravity है. Gravity कहती है कि एक gas है, if the mass of the gas is very large, for example in a star, the gas must collapse because of gravity, because the mass is bringing the gas together. But when the gas molecules come very close together, so close that the atoms start coming close together, then there are other external pressures that come into play. And one of those external pressures is quantum uncertainty. The quantum uncertainty principle prevents the electron from coming directly into the nucleus. So the quantum uncertainty is like an external pressure that acts on atoms. And it's purely of quantum origin. Now there is another very interesting application that I would like to mention. याद रखें, ये अनसर्टेनिटी प्रिंसिपल समझना मुश्किल है, मगर एक दफा समझ आ जाए तो फिर वारे ही नहीं आ रहे. समझ आ जाए, इसकी इतनी एप्लीकेशंस हैं कि आप तसव्वुर नहीं कर सकते. यहां तक कि ये जो अनसर्टेनिटी और रैंडमनेस है, ये डिटरमिन करती है हमारा डीएनए कोड एट द टाइम ऑफ फर्टिलाइजेशन. So the way we are human beings and the way we act and the way we look is, quantum mechanics is at the heart of it. Uncertainty is at the heart of it. Why do we have inflationary universes? Quantum uncertainty is at the heart of it. Why do atoms decay and give off radioactive energy? Quantum uncertainty lies at the heart of it. So quantum uncertainty really lies at the heart of many natural processes, including the way we are. Why I am Sabi Anwar and why you are the way you are. So really a very profound concept. Another application of uncertainty principle which is a bit more technical than the fancy examples that I gave you is that there is problem with Bohr's model. And what is the problem with Bohr's model? Suppose you have a nucleus and you have an orbit, a Bohr's orbit with quantum number n, so that the radius is Rn, and there is an orbit with quantum number n plus 1, radius Rn plus 1. Now we know that the radii are quantized according to the Bohr's principle. So, and the radii are given by four pi epsilon naught h bar squared me squared और यहाँ पे n आता है ना, या n squared. Now what Bohr postulated is that the electron is inside this orbit. यही बोर ने कहा था ना, the electron is inside this orbit or an electron can be inside this orbit, and the electron cannot be in between orbits. That was Bohr's postulate. So the electron is doomed by fate to move inside these orbits. So what Bohr actually did, he was confining the position of the electrons, and he did not know the consequences, the nasty consequences of his postulate, because the consequences make Bohr ideas fall to ground. Because if the electron is confined to this orbit, we are assuming that there is no uncertainty in the radius of the electron. And if the electron is confined to this orbit, we are assuming that there is no uncertainty in the position of the electron. We know for sure that it's at this particular radius. But that is not allowed by the uncertainty principle. So Bohr's model had a fundamental flaw. And Heisenberg in 1927, when he came up with the uncertainty principle, tried to remedy this flaw. And how do we show the inconsistency of Bohr? We simply assume that suppose the electron is confined in this radius, in this region. So still we are confining the electron to a narrow region, in between orbits, but we are being more generous than Bohr. Bohr said that the electron has to remain inside this orbit or this orbit. But let's be a bit more generous for the sake of calculation and assume that the electron is confined to the region in between these orbits. Still we are restricting the position of the particle. So now our uncertainty in the radius becomes Rn plus 1 minus Rn. ठीक है? 4 pi epsilon naught h bar squared me squared n plus 1 squared, which is n squared plus 1 plus 2n minus n squared. ठीक है? So ये n squares cancel हो गए. If n is large, we can assume 2n to be much larger than 1 and just forget about this one. So for large n, that is we are away from the nucleus, we have 4 pi epsilon naught h bar squared me squared 2n. Now this is the uncertainty in the radius. We can compute the uncertainty in the momentum because of the uncertainty principle. The uncertainty principle would tell us that the uncertainty in momentum is of the order of h bar over delta r. Now h bar over delta r would be given by me square eight pi epsilon naught h bar n. So this is the uncertainty in the momentum associated with a particle that is confined within this range of radii. This is the uncertainty in the momentum. Alright. So if there is an uncertainty in the momentum, there has to be an uncertainty in the energy as well. And if the electron is very far off from the nucleus, we can ignore its potential energy and assume that all of its energy is kinetic. That's what happens for an electron that is very far off from the nucleus. So its energy can be assumed to be purely kinetic, p squared over 2m. And the uncertainty in the energy will be 2p 2m delta p. just take the differential of this. We get P over m delta P, which is the velocity of the particle into delta P, the uncertainty in the energy. So the uncertainty in the energy is almost equal to, remember I'm using order, these tildes which represent that these are order of magnitude calculations, these are estimates. So delta E is of the order of V times delta P, and delta P we've already calculated, V me squared 8 pi epsilon naught h bar n. But the velocity of the particle, since the angular momentum is quantized, the velocity is also quantized, and from the Bohr's model we can tell what the velocity is. The velocity is quantized, you can prove this quite easily. The velocity is E squared over 4 pi epsilon naught h bar n. h bar n. इसको आप derive कर सकते हैं ना, because we know that L equals mvr is n over h bar. So V is n h bar over mr. You put in the value of r that comes from the Bohr's model, you can find the quantized form of the velocity of the electron. So now we have this expression. Remember, it's positive. We have me4 4 pi, in fact 32 pi squared epsilon naught squared h bar squared 1 over n squared. So this is the uncertainty in the energy. But from the Bohr's model, we know what the energy of the electron is in this particular orbit. We know that. And that energy is, the energy of the electron in the nth orbit is minus me4 over 32 pi squared epsilon naught squared h bar squared over 1 over n squared. Now the uncertainty in the energy is of the same order as the energy of the particle, of the electron in the nth orbit, which means that if the electron were in the nth orbit, it would have an uncertainty so high that the electron will be ionized. The electron cannot remain in that orbit. From Bohr's model, we know that the energy is quantized according to this relationship, but the uncertainty in the energy that we've calculated is of the same order as the energy, which means that the electron cannot be bound to the radius Rn. That is, the electron cannot exist at this radius, or it cannot exist within this region if we confine the electron. So what does this mean? This means that the ideas of Bohr's orbits is at best very flaky. अच्छा, थोड़ा सा टेक्निकल है. देखो, अनसर्टेनिटी इन एनर्जी मैंने ये निकाल लिया, ठीक है, ये अनसर्टेनिटी इन एनर्जी निकाल लिया मैंने यूजिंग अनसर्टेनिटी प्रिंसिपल. Now from Bohr's model, we know that if the electron is in the nth orbit, its energy is given by this. We know this from the Bohr's model. If it's in the n plus 1th orbit, you will replace n by n plus 1. But since n plus 1 is almost the same as n for very large n's, therefore this is the approximate energy of the electron. But now we have an uncertainty that is almost the same order. In fact, it's exactly identical to the energy, this expression. So this is the energy and this is the uncertainty in the energy. तो ये सारी की सारी एनर्जी अनसर्टन हो गई, जिसका मतलब ये देखो, अगर हम एक वैल्यू मेजर करते हैं 3, if we measure some, if you have a measurement, the length of this table is 3 feet, Now if the value is 3 feet and the uncertainty is 3 feet as well, we can never be sure of what the length of the table really is. So now we have an electron. Bohr told us from his postulates that the energy has to be this, it's quantized, but from uncertainty principle what we are observing that the uncertainty in energy is as large as the energy itself, which means that it is impossible to confine the electron within this narrow region. And if it's impossible to confine the electron in this region, it's even more impossible, it's even more ludicrous to confine the electron to this orbit, to confine the electron to any orbit. So the idea of Bohr orbits is at best flaky. There is a fundamental flaw, there is a fundamental limitation of these Bohr's orbits. And we should stop thinking that the electron is confined in these orbits. In fact, there is a field associated with the electron which spreads over entire space. The most probable position of the electron is at this orbit, but the electron can be really anywhere. And this is what we're going to study in the subsequent lectures. So thank you very much. I'll answer questions at the end.